The last two topics that we're going to discuss, scale differences in data and data discretization, both are data transformation topics. So we will transform the data into a new form so that it can be better processed by our learning algorithms or data cube navigation. So data are transformed or consolidated into forms appropriate for mining. So this is the goal of data transformation. So we actually have looked at quite a few already. Smoothing, right? Removing noise from data. Attribute and feature construction. Aggregation. We have discussed all of the three. And next, what we're going to discuss is normalization and discretization. Normalization is the process that we need to scale the data so it fell within often a smaller and specific range. The reason that we need to do normalization, we have mentioned multiple times, and by this time you should know it very clearly. So we're going to look at these three methods very commonly used. The first is min-max normalization. So your income, let's see, we're doing income data. Our income range is from 98,000 to from 12,000 to 98,000. We want to normalize this range to a smaller range, which is from 0 to 1, because we might have in many other numerical values like body height. We can have 1.6 meters, and 1.6 meters compared to this 12,000, they're in a different unit and they're in dramatically different scale. If we're doing any cluster analysis, that's going to give us a very, very skewed result, because the system is going to be heavily skewed towards income. Therefore, we want to normalize those, right? We normalize everything to 0 and 1, so it's easier for the computer. So we say that those things are roughly equally important. Help us to understand the data when we give you those normalized data. So the formula, the idea is very simple. We just need to map the original range to this smaller range proportionally. And we do it proportionally by using this formula. So I have one example here. It's very easy to follow. It's just commonly min-max normalization is either normalized between 0 and 1, or -1 to 1. But you can pick whatever range that you need. Typically, the range would be 0 to 1 and -1 to 1. Z-score normalization, we talked multiple times and we used multiple times, so we don't need to say it again. Normalization by decimal scaling, so which basically to still reduce this into a range of -1 and 1 by dividing the original number by a number that's power of 10. So here j is the smallest integer such that the maximum of the normalized value is less than or equals to 1. Using this to normalize this 50 and 20, we will pick j to be 2. Our normalization result would be 0.2 and 0.5 and 0.2. So both values are less than 1 or greater, less than or equal to 1. So that's normalization. It's fairly easy and quick. The next topic that we want to talk about is data discretization, used very often, in data preprocessing. So the idea is continuous attributes. So the attributes, you know, that takes a floating number or double number. When we do classification tasks on continuous variables, they often create a problem because we have for every attribute, the cardinality of that attribute is too large. You might have a let's see, if you have an income column that the position is down to dollars, then within a large database of 1,000 people, then you probably have 500 different income values. That will create a problem for many classification algorithms, for example, decision tree. So there is a need for us to discretize those attributes into intervals, so we can actually reduce the cardinality. We can break income to like low, mid, high, or we could break the income to under 50K, between 50 to 100K, 100K and 150K. So that will give us a smaller number of cardinality for the attribute, so it's easier to manage. When we do discretization, it also helps us to handle outliers and skewed data. For example, we can have a group of income that's less than 50K. Then if you have extremely small income, you are put in within this group. So you becomes kind of normal data point in this bin. Discretization can be done in a supervised or unsupervised way. We're going to look at unsupervised is fairly easy to understand. When we do a histogram, just cutting things using depth binning by equal width bin or equal depth bin, we're using unsupervised method. We're not giving any information. We just cut the data at some arbitrary points or at some points that's informed by domain knowledge, but not, we don't have labeled data. And we don't need labeled data to perform unsupervised discretization. Supervised discretization, on the other hand, do. For a classification task, if we want to discretize, for example, people's age, you can actually make use of the class label information to inform your discretization decision. Where do I cut? What ranges should form those intervals? So we're going to look at one example of supervised method, since it's probably new to many of you. And discretization can be performed recursively on an attribute. You can split this data range top down. First to large, small, and large. Then from the small, you can have very small, medium small, and some other smalls. And on the large side, you could have further divide your large group into some other additional groups. You could also take the merge approach, which is bottom up. We're going to see a bottom up approach example next. The goal of discretization, obviously, I think we hinted on this, is to prepare the data for future analysis. Data discretization methods. So all those methods can be applied recursively. So you can have different levels. It could, the reason that you sometimes want to do, have the data in different levels is because one, you might want to use data cube technology to allow drill down and roll up exploration. Other times is you don't have very clear idea what would be the best result to what kind of discretization strategy going to give you the best performance, and you do it at multiple levels and try them out and see uh, which discretization decisions give you the best performance. So we can use bin and histogram analysis. This we have discussed earlier. You can see fairly easily that it can be used for data discretization purposes. Clustering analysis, we also mentioned this before, right? Things within a cluster becomes can be labeled so that every data point in this cluster is replaced by the cluster label. So you actually discretized those values. Classification analysis, for example, decision tree. It's a supervised method because we know the class labels. It's a top-down split. Decision trees always goes top-down. When we talk about decision trees, you can see that decision tree can discretize your data automatically, so that it's after discretization, the data will be transformed in a way that's the best or easiest form to explain the class label distribution. I found that was a very long sentence, probably very difficult to understand. But okay, so let me give you the example to illustrate this idea. So in our police shooting data, we have victim's age, and we also have victim's race. And in one classification task, we were trying to predict race based on other data. And the decision tree was able to discretize our age attribute and made decisions on those age. So I think one of the rules that we drew, that decision tree learned, was if a person's age is greater than 26 years old, then this victim is likely to be a white, to have white race. If a person is under 26 years old, and if this person is in a highly populated location, for example, California, then this person is likely to be a Hispanic. So you can see when the decision tree was made, the algorithm can find the best cut in the age, find that 26 being a good cutting point, so that the data can be better fit into the class distribution. I hope this is helpful. Lastly, we can use correlation analysis to find the cutting points in a continuous range where how can we create the intervals to discretize data, which is chi-merge. I'm going to make a separate video just to introduce the concept and see how chi-merge work for data discretization.